Question 8, the dolphin question. Figure 11 shows the dolphin. There he is. Wonderful. Which of the following statements is a correct deduction from this information? So you've got a table here. Ooh, look at this. Hertz and kilohertz. That's going to come back to bite you, maybe. 200 hertz all the way down to 90 hertz there, etc, etc. You've got to figure out, do they emit infrasound, do they emit ultrasound? Well, we know that the range of sounds that we can hear is from 20 hertz to 20,000 hertz, or from 20 hertz to 20 kilohertz. 20 kilohertz, 20,000 hertz, same thing. That's our range. So if it emits infrasound, it's got to have a frequency less than 20 hertz. Let's see if any of them do. They do not. To produce ultrasound, it's got to be higher than the highest sound we can hear. It's got to be higher than 20 kilohertz. This table's in kilohertz. Are they all above 20? Yes, they are. So all 4 dolphins emit ultrasound, but none of them emit infrasound. So it's got to be B for that one. Question A2, frequency range. Now, they have been somewhat generous to you a little bit, perhaps, because they've given you a clue to help you avoid the pitfall that they have given you as well. So, sort of mean, sort of nice. They've said the frequency range of the sounds from dolphin W is 91.8 kilohertz. Let's have a look at W. There you go. Now, if you made the mistake that a lot of you made with this one, you'd have gone, oh, 200 minus 92, 108. So the range should be 108. It says 91.8, so that if you'd have checked that, that might have given you a bit of a clue that you'd missed something there. Of course, the thing that you missed if you got that question wrong, kilohertz and hertz, as we said. So in order to work out the range from dolphin X, you're going to have to make sure that they're both in kilohertz, because that's what the question is asking you to put in. So what have we got? Dolphin X, it says 100 hertz, all the way through to 120 kilohertz. 100 hertz, to turn it into kilohertz, there's 1000 hertz in a kilohertz, we need to divide by 1000. 0.1 kilohertz, 220 kilohertz, and now the problem becomes much, much easier. You just take one from the other. 120 minus 0.1 is going to give you 119.9 kilohertz. Okay. Question B, scientist records the sound the dolphin makes as it swims towards him, and then the dolphin stops swimming but continues making sound. And we've got to work out what's going to happen to the frequency and the wavelength. Now they've phrased this slightly different to what you'd usually be expecting for this sort of question, because often when we talk about this sort of thing, we're thinking about the Doppler effect. Often we're thinking about things moving away, or moving. What they're asking for you to do in this case is describe what happens when they stop moving. So let's have a look at the situation before, which means, excitingly, that I'm going to have to draw a dolphin. So, I genuinely don't know how to do this. They've got a big nose, haven't they? I almost feel like I should quit while I'm ahead, because that's actually, I'm quite proud of that. There's our dolphin. It's not going to work, we're going to need to have a tail, aren't we? Something like that. You know what? I'll take that. Here's our dolphin. At the moment, he's swimming towards us. Here he goes. Now, as you know from the Doppler effect, if something's coming towards you making waves, those waves are going to get squashed. So those waves are going to be something like that. And then if we were to look at these ones that are coming back, the gaps would be a lot bigger on the back than they are at the front, because he's kind of squashing. If we were going to draw that sort of, not with a dolphin, but with a point, which, let's be honest, would have been a lot easier to draw, it would look perhaps absolutely terrible. Dot, wavefront, wavefront. So this is what's happening. Our dot that's producing these waves is moving in this direction. These waves are bunching up, these waves are spreading out. So at the moment, our dolphin's coming towards us. We're experiencing these waves that are squashed together. Now, of course, what's going to happen when the dolphin stops is that he's going to continue, or indeed she, if it is a lady dolphin, is going to continue to produce these waves, but because he or she is not moving, we're not going to have any squashing. So the waves aren't going to be squashed anymore, and that's the key to answering this question. The waves are no longer being squashed because he stopped swimming, or indeed she has. So what we have to do is describe what's happened, what happens to the frequency and the wavelength. 2 marks, 2 different words there. We're going to hit both of them. What's going to happen to the wavelength? Well, the wavelength isn't going to be squashed anymore, so it's going to be bigger than it was before. It used to be squashed, now it's not. Now it's bigger. The frequency, well, when the wavelength was squashed, you were getting loads of waves per second because they were all bunched up. Now you're not anymore. So you're not getting loads of waves per second anymore. The frequency has decreased. Frequency is going to decrease, the wavelength is going to increase. There's your answer for part B. Okay, now part C, we have to explain how the dolphin uses sound waves to determine which of the 2 things near it is closer. You can use a diagram. You know what, I'm going to reuse this one because I seriously doubt I'm going to be able to draw the dolphin of that magnificence a second time. Okay, not swimming anymore. There we go. And the art is complete. So the dolphin's going to produce some waves. Like it says, you can draw a diagram to help you answer. So he's trying to find out, or she is trying to find out which object is closer. So let's draw a couple of objects. There's one. Here's another. So here's the general idea. The dolphin's going to produce some waves. It's going to bounce off here and it's going to come back. And it's the same with this one, so it's the waves are going to go out like this, they're going to bounce back off and reach the dolphin. The dolphin's going to know that this object is closer than this object because the echo comes back a lot quicker. And that's really all that you had to say, stroke draw. So we're at what, 8C, let's see if we can find the official mark scheme for this one. Oh guys, it's disappeared. This is very distressing. There we go. Okay, so we're looking for dolphin emits and receives, or you could just say receives because emits is in brackets. Reflected, or sound reflected from the objects. So from the diagram would have been enough to show that. The dolphin can work out the difference in time taken to receive the echo. If you talked about sort of how long it would take, then that's implying that. The sound received in a shorter time is from the nearer object, for that 3rd mark there. So the dolphin receives echoes from the object, or reflected waves from the object, which you can get from the diagram. Works out the difference in time between producing and receiving the wave, and then if it's a shorter time, the object must be closer to us. There we go. That just leaves one final question. And it is a relatively straightforward goodbye dolphin question with the wave equation, but with a cheeky kilohertz thing in there, so we're going to have to be a little bit careful with that. So we have a velocity of 1,530, reading is difficult, meters per second. The frequency of the wave is 1.2 kilohertz. Hang on a second, kilohertz, so let's change that straight away. That's going to be 1,200 hertz. We just multiplied that by 1,000 because there's 1,000 hertz in the kilohertz. And finally we've got to work out what the wavelength is, so that's our situation there. We're going to use our equation. I think earlier in the videos I used C equals F lambda. In GCSE we use V instead of C, but it means the same thing. So we're going to use our very funny symbol equation. Very funny symbol. There we go. We're trying to find out the wavelength, so it's going to be V over F. If you're using the formula triangle, let's flash that out so you can see. Wow, that was bad. Or alternatively, of course, if you were doing the rearranging thing, we know that V equals F lambda. So to work out lambda, divide both sides by F. V over F equals lambda. Good. So you're going to do the speed 1,530 meters per second. I really shouldn't have made that noise whilst being recorded. And F 1,200. So we're going to end up with doing 1530 over 1200, and that will give you your answer, which according to the mark scheme would have worked out to be 1.275 meters. There's your wavelength. 1.275 meters is the wavelength there. There we go.